I would just get right to it, I guess. So I am a physics student working on sort of the something intermediate between atomic and nuclear physics, and I was working with Bela in a network of 15 very nice PhD students, and I'm glad that I can present my research to you today. I try to make it as easy as possible, like not go too much into detail because I don't know what your background is, if there's maybe some people that did not study physics. But if there's some, I don't know, some questions that pop up, or if I went too fast or you want some more details, then just don't hesitate to stop me and I can give you some more information. So yeah, the main topic of my research that I do for my PhD is, as the title says, laser spectroscopy of the heaviest actinides. So I'm performing experiments with lasers on a very certain group of elements and then certain subgroup of elements, so to say. And this research is performed at the GSI Darmstadt Center in Darmstadt in Germany, which is not huge, but a big user facility, basically in the middle of Germany, similar like CERN, where the operators can supply the users with all kinds of beams, and it's pretty unique in that sense. So we have two, I hope you can also see my mouse, I just assume that you do. We have a couple of ion sources here. So here's the ion source, there's another ion source and another ion source, and then they have different kinds of ion sources also, so that they can basically supply the users with beams ranging from like made up from hydrogen, so like the lightest beams that you can have, and then up to uranium basically, and they can even supply it simultaneously, which is pretty amazing because similar experiments can be performed at the same time. And then coming from the ion sources, we have our big linear accelerator here, the UNILAC, that can supply these different branches here in the old experimental hall directly. But we also have an injection into a big ring accelerator, like a second acceleration stage, or the ion beams, where we can supply different storage ring experiments here, and then different parts of the fragment separator. As you might know, GSI is now undergoing a huge upgrade, so to say. So we're building a new facility that's called FAIR, and it will have an even bigger accelerator ring that will also enable more experiments. And here's also new storage rings that are going to be built for new experiments with antiprotons also. And with this new facility, we will also have access to even more exotic nuclei that we cannot access with the current facility of GSI. So it's pretty amazing. Every time that you just pass by the construction site, it's just growing and growing, and it's really impressive. So I think in the next couple of years, there's a lot of new stuff that will going to happen there. For the experiments that I'm performing, I'm sort of working at a very historically important place for GSI because I'm performing my experiments just after the ship separator. And that's like a large-scale device just in the straightforward direction from the UNILAC beam here. And this big separator is historically so important for GSI because that's the place where 6 new elements were investigated. So new elements ranging from boron, vanadium, vanadium to copernicium. These were first discovered just here at the ship separator, and GSI also contributed to the confirmation of findings of other new elements as well, also here at this place. And we're still performing experiments on heavy elements there, but we're not looking for new elements anymore because all up to organeson, everything has been discovered and confirmed, but we're still performing experiments towards the heaviest elements, so to say. And the element group that I'm sort of focusing my research on, that is a group of the actinides, which is the group of elements ranging from actinium all the way up to lawrencium. And probably for the general public, these elements are quite exotic and not well known. Maybe, I mean, uranium is commonly known, plutonium as well. Some people might have heard about thorium and americium maybe. But other than that, I think there's not much information in the general public. And one thing that is maybe also a little bit terrifying about these elements is that all of them are radioactive, which is usually not the nicest thing. For us, it's pretty interesting because these nuclei, because they're so unstable, have, of course, many more interesting things to study than the lighter elements, but it also makes the experiments more challenging and difficult at the same time. So in the range of the actinides, my research is focusing on the heaviest ones. So just here in the very end of these 14 elements. And the heaviest really meaning, if you would compare the weight of, let's say, a Lawrencium atom here, or nobelium, let's say, that's my example here. If you would weigh a nobelium atom and compare it to helium, it would be much heavier on the scale. And that's because in nobelium, there is 102 protons and then something like 152 neutrons there, while in helium nucleus, it might only be 2 protons and 2 neutrons. That's a lot less matter also in there. And studying the heaviest actinides is also interesting, or specifically interesting, because relativistic effects that will have an influence or will affect the properties of these elements are pronounced. And so if we want to investigate how these relativistic effects sort of alter the atomic structure, then it is very good to study this in the heaviest elements, because these effects are just much stronger there to being able to sort of quantify them. And all these experiments we perform with lasers. Lasers are a pretty awesome tool because we can find out so much about these elements. As I already mentioned, we can get information on the atomic structure and how relativistic effects alter the structure of heavy elements. Then we also get information on chemical behavior, for example, how chemical bonds can be formed with these heavy elements. We can also get information on the nuclear structure, for example, on the charge radius, how the charge distribution and the size of it is changing for different nuclei in these elements. And then we can also get information on the deformation of these nuclei, because not all nuclei are spherical. They could also be deformed and look more like a cigar, or like a football, or like a pancake, or something completely exotic. Is all possible, and we can sort of investigate that by shining in with our laser and then see if we can extract this information. Laser spectroscopy has been applied, especially to the actinides, a lot, especially in the recent years. And here you can see part of the nuclear chart, which is sort of like a map of all the different nuclei that exist. So look at here this row with uranium here. All these boxes here correspond to a different kind of nuclei of uranium. So these are isotopes, if you haven't heard this before. For example, here, this would be a uranium-238 isotope. So it has a certain number of protons. That's always the same for this element, but the neutron number might vary. And this, for example, here is uranium-235. It's the same element, but it will have 3 neutrons less. So it's a different isotope. And all these isotopes here in the nuclear chart that are marked in blue, they have already been investigated by means of laser spectroscopy. So especially here in the range of the lighter actinide, there was a lot of work already done, and much information was extracted. While comparing this to the range of the heaviest actinides, you can see that here for nobelium, for example, these red isotopes, they were only very recently investigated for the very first time experimentally. And for Lawrencium, there is no experimental information yet on none of the isotopes. And one reason for that certainly is that up to fermium, it is still not easy, but it's still doable to have reasonable sample sizes for laser spectroscopy experiments, like ranging up to, let's say, like you have picograms of sample sizes still that you can get from reactor breeding, which makes it easier to perform these experiments. While above fermium, you cannot access these nuclei from reactor breeding anymore, so you have to produce them at accelerator facilities like the GSI in Darmstadt. And then you're left with very low quantities of just production rates to begin with, and also very short lifetimes. That makes it, again, easy to, very hard to study these. So I thought we just go through the process, how such an experiment would look like. We now try to produce one of these Lawrencium elements, because apparently here is a lot of gaps that still want to be filled. Get first information on this exotic element. And then we look on lasers and how they can help us to extract this information. So first, how will we even produce this nuclei? It's pretty complicated because we have to sort of induce a fusion reaction. And at GSI, we can do this with the fast projectile beams that they can supply us with. So in this example, I picked a fusion reaction with a 48 calcium beam. And what we want at the end is we have 20 protons in this calcium, and we want something, a target that can help us to produce Lawrencium with 103 protons. So we have 20, we need 103. So the target needs then just the difference between them, so 83. And that is bismuth then. That's the target that we would need to create a Lawrencium. And I just wanted to show you how such a target looks like. So our targets are thin foil elements here, this foil here, based on a wheel. This beam that we get from the accelerator is super high energetic, and it will have a very destructive effect on the thin target foil. So in order to just distribute this destructive effect and to not just destroy the target immediately, we have a wheel that is rotating like at the same pace as there's beam pulses coming, so that we kind of extend the longevity of this target. There's quite some damage already done. So this a lot of beam here.
Jessica, your microphone appears to be, like, we can't hear you very well.
Oh, really?
Oh, can hear you now.
Oh, wow. That is weird.
Yeah, I'm not sure what it was.
Try to stay here.
Sorry.
No worries. Oh, wait, if you can't hear me. Okay. Was it okay? It's not okay to hear, or should I go back, or?
Maybe just a couple sentences go back.
Okay. Yeah, I thought it would be nice if I can show you a target on how these nuclei. This target has seen quite some beam, what you can see here in banana shape. And this target basically consists of just segments of thin foils of, it's not bismuth here, but it would be bismuth for the Lawrencium reaction. In order to, we just rotate it in the same pace as there's beam pulses coming in order to sort of distribute the destructive effect of the calcium over the target, because otherwise it would just be gone in a moment. So that helps us to keep this target and keep it alive for a longer time, as at least for a couple of days usually. And so with this calcium beam and the bismuth target, what we do is that this calcium beam is, as I said, highly energetic, and it will strike this bismuth target and just basically smash it. And these two nuclei here, calcium and bismuth, they will undergo a fusion process. So they will sort of meld together to a compound nucleus, which is a highly excited, super unstable nucleus that wants to sort of stabilize by emitting two neutrons, getting rid of these. And then we end up with like a de-excited, sort of stable nucleus, which is in that example now at 255 Lawrencium. So 255 minus 103 neutrons in there that we can perform our experiments with. This is the main idea, and the rate that we can achieve in this process, max is like 4 Lawrencium atoms per second, which is very, very little, because usually in experiments using, for example, uranium beams, uranium is naturally occurring on Earth, so you can have billions and billions of uranium atoms per second to perform the laser spectroscopy on. And for Lawrencium, we're left with 4 per second, which makes it very tricky, and the detection method needs to be extra efficient and sensitive. So yes, we have our lawrencium, and we would then send it to the experiment, separate it from the beam, like get rid of the remaining beam, and perform the laser spectroscopy on. But first, I think we need to have a look on how lasers actually work and what we can do with them. I think in all-day life, we meet laser applications maybe on a daily basis. So one of the main applications processing companies, for example, for laser welding or laser
Jessica?
lasers are also used for
I'm sorry, but
communication
you cut
with
out for a few
satellites,
seconds
for
there.
example. What?
You cut out for a few seconds there. Like we missed the start of the applications of lasers. You just went quiet.
Oh boy. Okay. I have no idea why this is. Okay.
Like just start from the start of like I think it went up to I think in everyday life lasers.
Okay. So I
Sorry.
just wanted to introduce you to some main applications of lasers. So I just wanted to make clear that lasers are used in our all day life, like for different applications. We would find them really in any situation because they're used so commonly. So one application, for example, is laser welding, drilling, marking. So like in machining and processing companies, lasers are used very often. And lasers can also be used for communication with satellites, for example. In more like the medicine and health field, lasers can also be used for eye surgery, for example, for tattoo removal and for all sorts of applications. And if you, that's more like an old-fashioned thing nowadays, but if you would listen to a CD, then lasers also help to read the information from the CD by scanning the pins on it and extract the data from the disk. And then, of course, lasers are used for research, and that is what we want to focus on today. To understand how lasers work, I just want to introduce you to the simple principle of it because it's very easy to understand, I think, because the main layout of every laser is the same. So to get started with a laser, we first need a laser medium, which is sort of the thing that is helping us to create the laser light. And depending on which laser medium you choose, you also choose the kind of laser light that you want to produce. This laser medium could be all sorts of things. It could be, for example, a solid, like a crystal, depending on which kind of crystal, it's different light that you can produce. It could be a dye, something that is fluorescing and allowing you to produce laser light. It could be gas or different things, really. But this laser medium needs to be supplied from an external pump energy to get started with the light emission process. And this pump energy could be, for example, another laser. It could also be a flash lamp or electric current that can help us to get started with this lasing process or the light emission. But then we also need amplification of the light that we emit to produce laser light. And this we gain by adding a cavity. So two mirrors around this laser medium that allow us to circulate the light here back and forth. And whenever the laser light or the light again passes the laser medium, we will have an amplification process. And if we come to a steady state where we cannot gain more energy because we will also have some losses, then we can couple out the laser light. So this mirror here will just reflect all the light that is coming to allowing this round trip for the light. While this mirror here is an output coupler, so it will also transmit some of the light to allow us to extract laser light from the cavity. And there we are. We have laser light and we can use it now. And with this, we want to shine light on our actinides and find out information on the atomic structure. The atom of an actinide is for sure much more complicated, but just to give you a simple idea on how it works is we have, of course, the nucleus in the middle, and then just considering your chemistry basis courses, basic course 101, you have the electrons sort of sitting on shells around the nucleus. And let's just consider this electron here, which we want to excite to study a atomic level. What we would do then, it's now sitting in a ground state. So here in the lowest possible energy level for this electron, and it wants to remain there. What we want to perform now is resonant ionization spectroscopies. So we want to first excite an electron to find out more about the level, but then we want to also ionize it because it's much easier to detect ions and to manipulate them and extract the information at the end then. So I thought I'd give you sort of a comparison. What the laser light does to the electron is the same as what we would do to a student. And since I'm German, I thought I just give you this cliche. So we excite the electron, and that's the same idea as giving a German student here. And then we end up exciting him. And that we also do with the electron. But what if the energy here, excited to this level where we want to go, is not enough to reach this state of excitation? It's not stable. So the electron cannot jump up to the next level. So what we need is more energy, or for the German student, we just need more beer. And then we reach this level and can push up the electron to the next level where it sits for a bit. It's not stable there, it wants to go down, but it will sit there for a while. What we want to do now is to ionize it, and that means the atom. That means we want to get rid of the electron totally and kick it out from the system. And we can reach that by applying a second laser here that will give all the energy necessary to push it above the ionization potential, because that is like a pretty good point from which the electron will not feel the attraction anymore and will just be removed. So we need a second laser, or we need some more wine, and that will give us enough energy to totally excite the atom, and now it's an ion and the electron is gone. This whole scheme here of this laser that we need for the first excitation step, bringing the electron here, and then finally, second step, removing it, this is pretty specific for each element and even for each isotope. So it's like a fingerprint, really, of this system that you're studying. And that also makes it possible to extract information if you, for example, want to find a level or try to investigate changes of this level for different isotopes. That's something that we can do with laser spectroscopy. How this looks like in the experiment is that we have the possibility to extract chemical properties. If we, for example, scan this laser, you would give it less energy so that it's sitting below the ionization potential here. And as you go higher and higher in energy and come over this threshold, you would have ions appearing because now it's enough energy to remove this electron. And it gives you information on where the ionization potential would be. And there's also on chemical properties, like what kind of bonds can be formed. Instead, if you leave this laser here with enough energy, you can also scan the first laser here, first excitation step. And just imagine you would start here below the level and then go towards the level. So then electrons start to occupy this level that can be ionized. And if you go above this level, then electrons stop to occupy this level again. So also the rate of ions that you see will decline again. And that is what we see in the experiment. As we come closer and closer to the level with the laser energy, we occupy it. We can see that now there's ions occurring. And if we go higher and higher in energy with the laser, then we stop occupying this level with electrons and there is no ions appearing anymore. This is how we can study this level and extract, this information on the atomic structure. And this has been done for many elements in the actinides until now, especially what you can see are the green and the orange lines. They show you all the different experimentally observed atomic levels that have been found so far. And especially for the lighter actinides, you can see that there's a lot of information. Apparently, all these lines levels that were already extracted. While in the range of the heaviest actinides here, for lawrencium, for example, there's only blue lines, meaning that it's only theoretical predictions that we have so far. There's no experimentally observed level. And even these theoretical predictions, it's very hard to perform them because these calculating these systems with that many particles inside the nucleus and the atomic shell is very complicated. That's why it's also tricky to try to perform your experiments with these theoretical predictions because the accuracy is not very good then. And compare lawrencium now to nobelium, then you can see that there is two levels, or here's highly excited levels, but we have this one level here, which was actually the first level found in the heaviest actinides only very few years ago. And that was a big success story, and we try to do the same now with lawrencium. So what they did back in 2016 was that they were just looking for this first level in nobelium with information that they have from theoretical predictions. So what they did was scanning the first laser and then see when ions would appear. And they were very lucky to see that because, of course, it's a tiny signal and a lot of background with very few ions that you have from the target in the first place. But they managed and they found the first level, and with that, they could not only extract information for 254 nobelium, that was the first isotope that they studied, but they could also go through a chain of isotopes and study the same transition for 253 nobelium and for 252 nobelium. And then you can see that they set off the center position for this atomic level is shifting. And this is due to the interplay of the nucleus with the atomic structure. And it gives you information on how the mean squared charge radius, for example, is changing. And with some input from atomic theory, even found that the 254 nobelium nucleus is not spherically shaped. It's more like a football-sized nucleus, and it even has a central depression here in the middle of the nucleus, meaning that there's actually more charge. Sort of theory calculations on the outer part of the nucleus than inside. So it's basically a bubble nuclei, and that's of course like a huge deal, big finding. And what you can see here in this splitting is not like two single levels in a sense, but for this nuclei there is an odd number of neutrons in there. Compared to the other two isotopes here and here, which introduces a splitting of this one level into two sublevels. And from that, you can also extract nuclear information again. So as I said, that was a huge success story. And the idea is to sort of try to find the same information on lawrencium, which is much more challenging because we have like a factor of 3-4 less ions to start off with, and the structure is more complicated. So wish me luck, but in lawrencium, the first level still needs to be found. So this was very nice, but it doesn't seem like, I don't know, maybe research on the actinide does have any influence on our all-day life, and that's probably the question that physicists get asked a lot, like how is this affecting society? What is this doing me any good? Well, for the actinides, there's actually a lot of applications, even though it doesn't seem so in the first place. So for actinium, for example, there's the possibility to apply the 225 isotope for cancer patients to treat them with targeted alpha therapy. So basically, you get treated with radiopharmaceuticals that can sort of fight, for example, metastases, because that's it's very hard to cure a patient from that. And some first tests that doctors did on patients with actinides that you can actually all these metastases appear by applying actinium. Then there's thorium, which is the second lightest actinide. And that's a very good candidate for nuclear clocks. There's a huge community around this performing research and trying to make this applicable at some point. But if they will be successful, then this would be like the most precise clock that you can imagine right now. And then there's uranium, which we all know and use in our all-day life, because power that we get from our sockets usually also have some part of nuclear power, and uranium is a fuel for nuclear power plants. There's also plutonium, which is not the best example for like good applications of science, but it also found its application. And americium, for example, was used for many, many years in smoke detectors. Not sure if it's still used, but that was a very, very handy application of an actinide. And it's also a good candidate for cancer treatment the same way as actinium. Californium is sort of a heavy actinide already, I think. This can be used to detect like problems in the metal frame of aircrafts by radiography. So you can find small problems before they grow to big problems in an aircraft, for example. So as you see in the lightest actinides, or the lighter actinides, there is quite some application even for our all-day life, which is very nice. And by performing more research on them, of course, we can find even more applications. For the heaviest actinides right now, it's really fundamental research that we do. But what it helps us with is to understand the heaviest elements. And there's a huge community towards the super heavy elements that wants to find out more about sort of the most unknown or exotic parts of the nuclear chart and the nuclear table. Because here in this nuclear chart, you can see all these black boxes, which means that these isotopes here are stable. And in the range of the heaviest actinides, there's nothing stable anymore, right? Everything seems super unstable and radioactive, and we can go all the way up to organeson here, which is the heaviest element. There are some theoretical predictions that there is sort of like an island of stability existing here in like for a group of isotopes here in the range of the very heaviest elements. And these predictions say that for this group of isotopes, there might be half-lives of something like ranging from seconds to days or even to thousands of years. It's very hard to predict. But if this would be the case and people would actually find this stable area again in the very, very exotic part of the nuclear chart, it might mean that our periodic table is not even ending here. It might be that organeson or these super heavy elements here are not the end of our periodic table, but it might actually continue afterwards if there's more stable nucleates in the nuclear chart. And with our research on like, the heaviest actinides and then aiming for the transactinides, of course, also, we try to get more information on how these nuclei can exist and on the nuclear shell structure, so that we can also sort of join this journey towards the island of stability. But as I said, so far there's no application to the heaviest actinides, but we never know. And I thought if you're interested in this whole actinide topic and also trying to coming to an end, we have a whole consortium of 15 PhD students that perform different kinds of experiments on the actinides, ranging from, for example, the applications of actinium for cancer treatment, then to other applications and to very fundamental research. And I thought if you're interested in that and want to follow us, we are on all social media platforms, and we also have different events, I think, in the pipeline, and maybe we can sort of attract you as a follower and meet you in one of these events. I hope we can have some, depending on Corona, but yeah, I hope we could give you an introduction to this research that we're doing. It's pretty unique in that sense. It cannot really be done in different places in the world, but I think it's super interesting.